(-1 and 0, right? It's leveling off. Okay? And then I appear to be increasing again from 2 to infinity. Sweet. I'm already halfway done. How about decreasing? Well, it appears from -infinity to -1, non-inclusive at both, right? Union from 0 to 2. Okay? Now, this max-min thing is going to take a little bit of work. What do we know for sure that that value is? It's going to be a min. But I don't know if it's the, I mean, I could have screwed up when I drew this thing. I don't know if it's the absolute min or is it a relative min? I don't know. And this guy right here appears to be a max. And then this guy right here appears to be a min. But I don't know which is which. Okay? We know for sure that this max, this thing's polynomial, which implies that this function is going to take off on both ends and go to positive infinity. So I know for sure that I have a relative max. I have a rel max. Pardon my notes here. I know I'm going to have a relative max. It can't be an absolute max because it's polynomial and things are going to blow up and go to infinity. I don't have any weird asymptotic behavior, right? So I have a relative max at where? At x equals 0 and f of 0. I'm going to just name the point, which happens also to be what? 0, comma, 5. That's a relative max right there. Nothing to it. All right, now I need to check some work out here because these min are special. They're going to give us a lot of, oh, I'm going to run out of room. I'm going to have to flip back and forth for pages. I apologize for that, but that's okay. All right, so what do I have? Well, let's check. I know that f of, where are we? -1. Now remember, I'm looking for the function, not the derivative. I know what f prime of -1 is. It's 0. So really I'm plugging it back into here. Let's do this over here. I know that f of -1 is equal to what? 3 plus 4 minus 12 plus 5. Wow, that's weird. So that smells like, to me, 0, right? I know that f of 2 is equal to what? 48 minus 32. Yell at me if I screw these up in class. Minus 48 plus 5, right? Let me double check that. Let's see. 2 to the 4th is 16. 3 6 is 48. 8 by 32 minus 48. These guys cancel. Yeah, I'm good, right? So negative 32. This is negative 27. So guess what? This guy is a relative min. I just check them by plugging them in. And this guy is the absolute min. Look at that. So over here, I can write that out. Let's get rid of this f of -1 because I already did the note work over here. I'm going to scream and yell and wave my hands and drive you guys nuts. However, I want your answers. I want things written cleanly. Okay, if you got a bunch of stuff floating around, I'm going to cry mathematical jellyfish, and I'm going to throw sharp objects around the room. I'm not really going to do that. That would cost me a job. Okay, so I know that I have a relative min at, what did we say, -1, comma 0. And I know that I have an absolute min at, I'm going to use a little and dealio, at 2, comma 27. Easiest falling in love, isn't it? Nice. I have milked this derivative for all it's worth. It's done. Now, what do I need for those guys? What do I need for those guys? Well, you guessed it. I'm going to need a second derivative. So let's write f of x equals, what was it? Let's see if I can remember, 12x cubed minus 12x. That's not right. What the heck is going on? That's my first derivative. I guess if we've got the first derivative, we're in good shape. Minus 12x squared minus 24x. Wasn't that it? 24x. Let me check. See if I remember. 12x cubed minus 12x squared minus 24x. So we're looking pretty good. Perfect. Okay. Now, remember, keep your eye on the prize. I'm looking for concavity and inflection points. Well, that's easy, right? Take a second derivative. That's what the second derivative is built for, to tell us about things like concavity and inflection points. So I got 36x squared minus 24x minus 24. What do I do? Set it equal to 0. Why do I do that? So I can solve for critical points, right? Always. Remember, critical points defined as any place where the first derivative equals 0 or isn't defined. And by setting it equal to 0, that gets me halfway home. Okay, if I factor out a 12, so this equals 12 times x squared minus 2x minus 2, right? 2x minus 2, right? And there's that. Unfortunately, this guy doesn't factor, does it? So what am I going to end? Oops, that should be a 3x squared. Sorry about that. That's not going to factor because there aren't any factors of -6 that add up to -2, right? 2, 3 is going to be -1 or a +1 or 1, 6, which is going to be a 5 or -5. So, bummer. However, in the handy-dandy world of technology, think of it like a cooking show. I already did the heavy work for you. Look at that. Oh, I should probably prove where that came from, right? I know I'm going to get a critical point at x equals, well, this doesn't produce any critical points, but it has a sign, so I'm going to keep it there because otherwise I'll lose my mind, right? So let's see, -a, that's going to be 2, plus or minus the square root of b squared, which is 4, plus 4 times 2 times 3, because the negatives cancel out, right? And I get, what, 28? This is 28, and this is divided by 2a, which is 6. This can be reduced to, what, 1 plus or minus. If I factor a 4, 4 times a, get a 2. That cancels. I end up with root 7 all over 3. So if I go over here, look at this. Oh, it's sitting there for me. All right? So 1 plus root 7 over 3 is approximately 1.215. 1 minus root 7 divided by 3 is approximately -0.549. Now, remember, when we're approximating in calculus, we want to go out to approximately thousands, or not approximately thousands. We want to go out to thousands. So I'm going to go 1.215 and -0.549. What do I do next? Well, you guessed it. Ripley doodle diagram, best thing ever. So f double prime of x. Remember, get that name on there. That's really, really important. I'll show you why in a second. So -0.549. It tells us what to plug into. We know what second derivatives tell us. They tell us about concavity. They also tell us, excuse me, they tell us about inflection points. Remember where concavity changes? All right? We're going to more clearly define inflection points in class. We'll play with all of those to make sure you got it. So, you ready? I'm going to find a value to the left of -0.549. I'm not going to be a smart aleck on this one. If I plug in x equals -1, well, if I plug x equals -1 into just 12, it's always going to be positive, right? So that first term's always going to be positive. Let's see. If I plug x equals -1 into here, I'm going to get 3, plus 2 is 5. Minus 2 is 3, so that's another positive. Guess what? I'm positive there. How about x equals 0? Again, you will get in the habit of doing these on your own, okay? In your head. You don't have to think about them. If I throw x equals, well, the first is always positive. 0 minus 0 minus 2, it's going to be negative, so this guy's negative. And then how about x equals 2? Again, the first term's always positive because it's positive 12. If I throw this in, what do I get? I get 12 minus 4 is 8. Minus 2 is 6. Last I checked. That's positive. Now, what does this tell us about f of x? Well, when the first derivative, when the second derivative is positive, I'm concave up. When the second derivative is negative, I'm concave down and concave up. Isn't that nice? Now, check it out. I'm going to call this, by the way, what it is when I do this over here, right? When I want to figure out when it's concave up, I know that I'm concave up. Let's see, what was it? It was from -infinity to 1 minus root 7 thirds, right? Because of my doodle diagram, look. See, right here, -infinity to this guy right here comes from the minus, correct? And then union 1 plus root 7 thirds to infinity. Concave down was between the two. So 1 minus root 7 thirds to 1 plus root 7 thirds. Be careful in interval notation. It can start looking like points, and it's not a point. Okay, now let's go back. Let's talk about, I'm going to change colors here. Let's go to orange. An inflection point. Let's clearly define an inflection point. An inflection point. We already did, but let's review it. An inflection point is a point on the graph of f of x, it has to be there on the graph of x where concavity changes. And I think when I showed you guys this before, remember I took 1 over x and 1 over x, and it was concave down to the left of 0, and it was concave up to the right of 0. The problem is that f of 0 doesn't exist. So there is no inflection point in this. However, there clearly is an inflection point here and here. We know that polynomials are defined for all values. So I'm only going to, because I'm lazy, I'm going to write IPs at x equals 1 minus root 7, comma 3, and x equals 1 plus root 7 thirds. Okay? Now, let's do a real quick sketch here. Nothing to it, just quick and easy. You ready? I'm just going to throw this thing in. It's not going to be drawn to scale, okay? What do I know? I know that, let's look at our maxes first. I know at 0, 5, so I'm just going to name this thing 0, 5, okay? And then, let's make this a little bigger so I'm kind of out of my own way. 0, 5, what else do I know? I know there's a relative min at -1, 0, so I'm going to put that guy right there. And then I know there's an absolute min at 2, let's call this 2, and then way the heck down here, right? I know the thing decreases from -infinity to -1. So I know that the function comes in and does that, right? Then what else does it do? Oh, it increases from -1 to 0, which it should. So it's going to go here and level off. Now remember, my scale's off, so this is going to look a little funky, right? And then let's see, then it decreases from 0 to 2, which is way down here. Remember, there's a point down here at 2, -27. That should be a negative, by the way. Did I put -27? That should be a negative. So sorry about that. So this guy goes way down here, right? However, it's an absolute min, so it levels off. It's hard to draw with the thingy, and then up it goes. This is about what f of x looks like. Now, wait. Let's be careful. Remember, this guy was about -0.5, and this guy was about 1.2. Let's check. You ready? This is -1 right here. This is x equals -1. This thing changes concavity from concave up to, whoop, right about there. Look at that, at about -0.5. It changes concavity again. Let's see, I was concave down here, so I went from concave up to concave down, and then it appears, even with my cruddy drawing, that happens about right there. Well, remember, this is x equals 2, so it appears that that happens at approximately 1.2. Look at that. Even with a bad drawing, we can do good stuff. All right, now I'm going to compare this. Let's shrink this thing down. I'm going to compare this to the actual function. So let's grab the function. I'm going to go y equals, oh, I got to clear some stuff out here, don't I? Clear. And we're going to go y equals, this is going to be 3x to the 4th minus 4x cubed, minus 4x cubed, and then, let's see, minus 12x squared, minus 12x squared, and then plus 5. And I'm going to just go zoom standard. No, I can't go zoom standard, can I? I got to tweak my window. So, well, let's go zoom standard first. Let's check everything. Y equals, okay, so we're in y equals. Let's just go zoom standard and see what happens. We know we're going to run into trouble with that -27, but let's see. Boom, boom. Hey, that's kind of cool. Look at that. Oh, look at that. That's really good, isn't it? How about let's tweak my window so that my y min is -30. So -30. And let's see that guy. Whoops. I want to see this guy. Grab it. All right. Look at that. That's great. We did a good job. Okay. Ladies and gentlemen, that's it. We're going to talk more and more. We're going to do so many of these, it's going to drive you nuts.